So in the last lecture we were considering the momentum balance in the x direction, and we are able to write the left hand side of the terms which represent the rate of accumulation and the net outflow of momentum. And we said that the rate of accumulation of momentum in the x direction plus the net outflow of x momentum through the control volume is equal to all the sum of all the external forces acting in the x direction. So today we have to specify what those external forces are so that we can complete the mathematical formulation of the momentum balance equation. So let us just see where we are for a control volume like this with a x length of delta x, a y length of delta y, and a z length of delta z, with velocity components u in the x direction, v in the y direction, and w in the z direction. We wrote that the statement of momentum balance in the x direction could be expressed as partial derivative with respect to time of rho u, which represents the net rate of accumulation per unit volume in this, plus partial derivative with respect to x of rho u square, plus partial derivative with respect to y of rho u v, plus partial derivative with respect to z of rho u w is equal to sum of all external forces acting in the x direction. So this was the relation that we have derived, and this statement, this equation is incomplete without specifying what the external forces are. Now what kind of external forces can we think of acting on this domain, on this small domain which has small lengths delta x, delta y, delta z, and which is one element of the entire fluid domain. So we are looking at forces which are present everywhere in the fluid, not at the boundaries as coming as boundary conditions and so on. So what kind of forces can we imagine? When we consider fluids, we already know that there is something called pressure, and so we can imagine pressure as a force which is acting on this, on a fluid element, and we know that pressure is a compressive stress. If you imagine a plane like this and it is immersed in the fluid above it and around it will be exerting a compressive stress on this, which is normal to the surface area vector of this particular plane. Okay, so in that sense pressure is a compressive stress. We also know another force which is the gravitational force, which is present everywhere. So we can consider gravitational force which is mg, and which we can write as rho times delta x, delta y, delta z times g. We can consider pressure force, pressure being an inherent property of the fluid. There is a difference between a gravitational force, which is a volumetric force which is spread throughout the domain, and a pressure force which is a force exerted on a surface, which is normal compressive stress. And if we imagine, for example, this particular plane which has an outward normal vector oriented in the positive x direction coming out like this, then the fluid which is external to this control volume will be exerting a compressive stress which is acting in the opposite direction along the same outward normal directional vector, but acting in the opposite direction. If we consider this top surface, the outward normal vector is oriented in the positive y direction, the fluid above it, that is external to the control volume, will be exerting a pressure which is acting downwards, and it is a compressive stress acting on this particular plane. So the fluid which is external to the body will be exerting a pressure against each of the 6 control planes, the 6 sides of this control volume, and that is what we mean by this pressure force. So we would like to distinguish between a gravitational force, which is a body force which is acting, which is essentially the acting on every fluid particle which is contained within this, and the pressure force which is acting only on the surfaces of the body by the fluid external to this. Now, is there any other force? We know that a fluid has a property called viscosity. Viscosity is we call it as a flow resistance offered by the fluid to relative motion, and the simplest form is that the shear stress is equal to mu du by dy is what is considered as the Newton's law of viscosity, where this shear stress causes a gradient of velocity or a strain rate which is given by du by dy, and it is made proportional to this. What this actually means is that one can interpret it as a relative velocity, okay, velocity gradient here will induce a stress which is governed by the viscosity. So one can say that a fluid will have viscous forces in addition to the pressure force and gravitational force. Okay, so we have as the third element viscous forces. Just like pressure forces are normal compressive stresses acting on the stress, viscous forces are also arising from viscous stress. Because this shear stress is actually a stress. So what we can see from this, in addition to this, we may have, for example, for a magnetically conducting fluid, we may have magnetic forces and electromagnetic forces and other forces which may be coming into picture, but we restrict our attention to simple fluids without any extra effects. So we can consider these as the main forces that are acting on this, and you can say that surface tension is a force that we have to consider, and it is an inherent property of the fluid. But surface tension is a force which appears only at something like an air water interface, only at the edge of the boundary. Okay, it is not inside in the interior of the fluid continuum, and we are talking about a fluid control volume which is everywhere within the fluid continuum. So unless you have an air water liquid air liquid interface at this point or within this control volume, we need not consider surface tension. So surface tension would come up as a boundary condition rather than as a force within this within these considerations. Okay, so from looking at these things, when we talk about a general framework for external forces, we see that we have to distinguish between two types of forces, those that are body forces and those that are stresses. So we can say that external force is a type of body force plus a stress. Okay. Now we have to be careful with the stress, because stress times a particular area is what will give rise to a force here. Okay. So we have a body force and a stresses. We will evaluate both of these separately, and among the body forces we consider gravitational force, which we know is mg. So this is rho delta x delta y delta z times g. So when we talk about the body force here, F body force is nothing but F gravitational. So, this is rho delta x delta y delta z times g, and when we take the we have forgotten here divided by delta x delta y delta z, and in the limit as delta x tends to 0 and all these things. Okay, so, now the equivalent gravitational force in the limit of this divided by delta x delta y delta z going to 0. Okay, so, we can say that F body divided by the volume in the limit as delta x tends to 0, delta y tends to 0, delta z tends to 0 is nothing but rho g, because this cancels out and we are left with this, and specifically the x component of the body force per unit volume is rho g x. Okay. So, where g x is the x component of the gravitational vector. So, from that point of view, when we consider the momentum balance equation and when we want to look at the external forces acting per unit volume of the control volume, then this is nothing but rho g x for the body force which we are identifying as the gravitational force. Now, what about stresses? Stresses which are coming from the inherent property of the viscosity or from the inherent fluid property of the pressure. So, as of now we treat them together in stress tensor sigma, because we need to consider that when we are looking at a body like this, 3-dimensional body like this, the stress is a tensor which is acting on all the faces, and we have to identify this properly, and we have to have an established notion of what stress is. If we imagine a surface like this, a plane surface, then we can have a stress which is oriented onto this normal to the stress, normal to the surface. We can have a stress in the plane of the stress, for example in this direction or in this direction. Okay, so, we can, for every surface we can have 3 stress components, one which is normal to the surface. If it is positive, then it will be like this, if it is negative, it will be going into the surface, and a stress which is perpendicular to this direction. For example, if this is x, then this may be y direction, and the stress which is x direction and z direction. So, we can have stress, normal stress, and 2 shear stress components which are trying to deform the plane. Okay. So, for every plane, if we come here, we can have a normal stress, and we can have a stress acting in the y direction, and we can have a stress acting in the z direction. When you come to this surface, again you can have a normal stress acting in this direction, and a stress acting in this direction, and a stress acting in this direction. So, for every surface we can imagine 3 types of stresses, one normal stress and 2 shear stress components, and we see that the normal stress component for this plane and the one of the shear stress components for this plane are in the same x direction. Okay. And if you consider, for example, this plane here, this front face, you have a normal stress coming in this and a shear stress coming in this direction and in this direction. So, each face has 3 components, and we have to, when we talk about a stress acting on a surface, we have to identify on what surface it is acting and in which direction it is acting on the particular surface. So, the stress tensor here is identified with two subscripts which we call as I and j, and where this implies the stress acting on the ith plane in the jth direction. So this is the convention that we follow, and using this definition we can now put names to these stress components. When we consider this particular phase, it has an outward normal vector which is aligned in the positive x direction. It is aligned in this. So we call this as the x phase. So this ith phase here refers to the outward the direction in which the outward normal vector is aligned. Okay, so this is an ith this is an x phase, and because the outward normal vector is aligned in the positive x direction, that is a positive x phase. So this component, this stress here is aligned in the x direction, so this j here is x. So when we talk about this sigma here, the I is x and j is also x because this particular component is acting in the x direction. When we look at this component here, this is acting on the same x phase, so this is sigma x, and it is acting in the y direction. Okay, so that is sigma xy, and this component here is acting on the x phase, so sigma x, and it is acting in the z direction, sigma z xz. Now when you come to this, this is acting on the y phase because the outward normal vector is aligned in the positive y direction, so this is a positive y phase, so this is sigma y, and this particular component is acting in the y direction, so that is sigma yy. This component here is again acting on the positive y phase, so the first subscript is y, sigma y, and this is acting in the x direction, so this is sigma yx, and this component here is again acting in the positive y direction, positive y phase, so sigma y, and it is acting in the z direction, so this is sigma yz. Okay, so we can see that each component here specifies what phase it is acting in and in what direction that is acting in, and by convention we also indicate whether for a control volume like this, we also include in the notation here, in the convention here, the distinction between a positive x phase and a negative x phase. For example, if you consider this phase here, that is the left side phase of this, left, right, bottom, top, back and front. So on this particular phase, the outward normal vector is aligned in the negative x direction. Okay, so this is the normal vector of this particular phase, and so this is aligned in the negative x direction because positive x direction is in this direction. So this is a negative x phase, and on a negative x phase the normal stress will be just okay. So this will be acting, this is again x phase because this is obviously an x phase, and it is acting in the x direction, but its direction is in the negative x direction. Okay, so instead of being in the positive x direction, it will be considered to be acting in the negative x direction, and the y directional stress on this is supposed to be down. Okay, so this is sigma xy, and this is acting in the negative y direction because it is a negative x phase, and similarly the xz component will be acting in this direction. Okay, so this is sigma xz, so x indicating the phase on which it is acting and z indicating the direction which it is acting, but for this particular control volume this happens by negative phase, so it is acting this acting in the negative z direction, and this acting in the negative y direction. So we can see that out of we have 3 positive faces and 3 negative faces. On the positive face, the 3 stress components act in the positive directions of the coordinate faces, like sigma xx positive x direction, sigma xy acting in the positive y direction, sigma xz acting in the positive z direction. But on the negative face, for example this one, sigma xx is acting in the negative x direction, and sigma xy is acting in the negative y direction downwards here, and sigma xz is acting in the negative z direction. If you consider the bottom face here, okay, so this component here is sigma y y, because this is a negative y face, and y indicates the second y indicates the direction which it is acting. It should be acting in the y direction, so ideally it should be upwards, but because it is a negative y face we put it down. And correspondingly sigma, this plane y plane will also have a sigma yx component and a sigma yz component, which are the 2 shear stresses, and because it is a negative y face, sigma yx will be acting in this direction and sigma yz will be acting in this direction. Okay, so when we consider a 3-dimensional a cube like this, then on each of the 6 faces there are 3 stress components, and these are acting, and out of the 3 stress components, one is in the one is a normal stress, the other 2 are shear stresses, and the notation here sigma ij here has a convention that I indicates the outward normal vector of that particular surface on which the stress is acting, and j indicates the direction in which that particular stress component is supposed to act. Okay, and in the general case, when we want to consider a stress acting on a 6-sided figure like this, there are 18 components. When we do the momentum balance in the x direction, we are not interested in the forces acting in the y direction. For example, the stress which is sigma yy is acting in the y direction, sigma yz here is acting in the z direction. We are not interested in stresses acting in the y direction or the z direction. We are interested only in those stresses which are acting in the x direction, that is those stresses for which j is equal to x. For example, this sigma yx here, it is acting in the x direction, this sigma xx is acting in the x direction, this sigma xx is acting in the x direction, negative direction, but still it is acting in the x direction, this sigma yx is acting negative x direction, and okay, we have not here we have a sigma zx which is acting in the x direction. So as far as the momentum balance in the x direction is concerned, apart from the body forces, when we consider the stress forces here, we have to consider only those stresses which are acting in the x direction. There are 18 stresses, out of which 6 stresses are acting in the x direction and 6 in the y direction, 6 in the z direction. Now let us identify the stress components acting in the x direction. We follow the same notation that this is x, this is y, and this is z direction. So when we consider this face, that is the right hand side face, the stress acting is sigma xx, and we put the origin here, and this particular plane is at a distance of x naught plus delta x distance. So we can write this as x naught plus delta x, and the stress acting on the top surface in the x direction, that is from here it is acting in this direction, and this is sigma yx, and this is acting in the plane which is located at y naught plus delta y, and that is acting in the positive x direction. When we consider this front face here, this again has, this is a z face and it has a stress acting in the positive x direction, and this is sigma zx because this is acting in the z plane, and it is acting at on the plane which is located at z naught plus delta z. Now let us consider the negative faces. So this face, which is the left face, has a stress acting in the x direction, that is sigma xx at x naught, and is acting in the negative x direction, and the bottom face here has a stress acting in the negative x direction, and this is sigma yx because it is acting on the bottom face, that is a y face, and it is acting in the x direction, and this is at a plane, y plane, which is located at y naught. And now we consider the back face. This again is a negative face because the outward normal vector is aligned in the negative z direction. So this has an x component which is acting like this, and this is sigma zx on a plane on a z plane located at z naught. So these are the stress components, and we know that each surface here is a plane with either delta x, delta y, delta z as the dimensions. So using this we can now compute the external stresses acting in the x direction by multiplying each stress component by the corresponding area, and because we have taken these planes to be aligned with the normal directions, then this dot product becomes very easy. So we multiply the corresponding stress with the area, and then we can therefore write f external x sum of all external x as we have already got rho g x times delta x, delta y, delta z, that is the body force, and we now have to evaluate each stress and multiply by the corresponding area. So let us first consider the sigma x axis. Okay, so we can say if we consider this, then we get sigma xx at x naught plus delta x times the area, which is delta y, delta z, and on the opposite face, that is on the left face, we have a sigma xx, and it is acting in the negative x direction. So that will be with a minus sign, minus sigma xx, and now this is at x naught and an area of delta y, delta z, and then we have plus the top face, which is sigma yx at y naught plus delta y times the corresponding area, which is delta x, delta z, minus sigma yx at y naught, which is on the bottom face acting in the x direction, times delta x, delta z, plus the stress acting in the front face in the x direction, so that is sigma zx at z naught plus delta z times the area, which is delta x times delta y, minus sigma zx at z naught, which is the back face, times delta x, delta y. So we have the external forces as the gravitational component and 6 stress components acting on the 6 planes in the x direction multiplied by the respective areas. Now what we want is the sum of all these forces on a unit volumetric basis in the limit as delta x, delta y, delta z tend to 0. So we divide this whole thing by delta x, delta y, delta z, and take the limit as delta x, delta y, delta z tend to 0. Now let us before we take the limits, let us try to simplify. So as we have seen earlier, they cancel out here, delta y, delta z cancel out from this, and we are left with delta x, and here delta x will cancel out and delta z will also cancel out. We are left with delta y here, and here we are left with delta z. Now if you take the limit as delta x tends to 0, delta y tends to 0, delta z tends to 0. So that is, we are considering a smaller and smaller and smaller volume of this particular unit volume. This thing here becomes rho g x, and this is sigma xx. Let us say it is a variable at x plus delta x naught plus delta x minus the same variable at x naught divided by delta x, as x delta x tends to 0 is nothing but the derivative of that particular quantity in the x direction. So this is dou by dou x of sigma xx, okay. And this one here is again sigma yx at y naught plus delta y minus the same quantity sigma yx at y naught divided by delta y, as in the limit as delta y tends to 0 will give us variation with respect to y of sigma yx, and this gives us plus dou by dou z of sigma zx. Okay, so the left hand side, the right hand side term in the momentum balance equation now can be written like this. So this is equal to what we have on the left hand side, so that we can write down the complete momentum balance in the x direction as d by dt of rho u plus d by dx of rho u square plus d by dy of rho u v plus d by dz of rho u w equal to d by dx of sigma xx plus d by dy of sigma yx plus d by dz of sigma zx plus rho gx. This is the x momentum balance, and we can similarly write the y momentum balance by doing exactly the same thing. We look at the rate of accumulation of the y momentum in this and the rate of inflow of y momentum through the x face and y through the left face and bottom face and the back face, and we evaluate the rate of outflow of momentum through the right face, the top face and the front face, and then we evaluate also the forces acting on the body, okay, on this control volume, like the body force, the gravitational force as a body force, and the various stress components acting in this, and we can divide those whole thing by delta x, delta y, delta z, and take the limit as these things tend to 0, so that we are considering almost a point, and at that point we can get an equation very similar to this. Instead of u here we have v, and one of the u's becomes v here, dou y of rho v square plus dou by dou z of rho v w equal to dou by dou x of now sigma x y plus dou by dou y of sigma yy plus dou by dou z of sigma zy plus rho gy. Okay, so this is the y momentum balance. When you compare the two, you see that the stresses that are appearing in the x momentum balance all have x as the second index, because that indicates the direction in which that particular stress component is acting. So in the x momentum balance equation, that second index must be x, and in the y momentum balance the second index, that is sigma xy here, sigma yy and sigma zy, that is in the y direction, because we are representing the y momentum balance. And we can write a similar expression for the z momentum balance equation. So this completes the derivation of the momentum balance in the x, y, z directions. So now what have we got from this? The force balance in the three directions, in the momentum balance has given us three extra equations, and the three extra equations are the momentum balance in the x direction, momentum balance in the y direction, and a similar equation for momentum balance in the z direction. And we also have one equation for the continuity equation, which we have derived in the previous lecture. So now we have four equations. Okay, and what are the variables that are appearing in this equation? Let us just see. When you consider this, u is obviously one variable, u is a variable, v is another variable, w is another variable, and we still have to specify what these stresses are: sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. So the variables that are appearing in these four equations are, there are 9 stresses plus 3, that is 12, out of which we have, for these 12 variables, we have only 4 equations. Equations are, one is the continuity equation, x momentum balance equation, y momentum balance equation, and z momentum balance equation. Okay, so we are faced with the tricky situation that we have far fewer number of equations to describe the variables that are appearing in this. We can say that we have additional equations like the energy equation. We have not imposed the energy equation, but energy equation obviously brings in a new variable, which is the enthalpy or the temperature. We can bring in one more equation, the entropy balance equation, that brings in one more variable, so which is the entropy. So by adding more number of equations, we are not resolving this imbalance between the number of equations available and the number of variables that are appearing in these things. Okay, so this kind of imbalance, okay, is something that cannot be just resolved by adding more number of equations, okay, more number of fundamental equations, and we have to bring in empiricism. We have to bring in some kind of expectation of the fluid behavior to describe what these stresses are. The major problem is coming from the stress components. There are 9 of those stress components. Unless we specify what we mean by the stress components, we cannot hope to get a balanced number of equations and a number of variables. Okay, so we need to instill more information into a model, especially in the form of what these stresses are, so that we can hope to get as many equations as the number of variables there are. And we need to bring in some sort of conception of the stresses that are appearing within the fluid. Okay, so we need to have some sort of constitutive model, a model which describes the constitution of the fluid in terms of what kind of stresses, and one such constitutive model is this. This stress is one of the stresses that we are considering. Okay, and although we have put it as tau here and we have put it as sigma here, one can say that the tau, this is also a stress which is a viscous stress, and this has been related here through a viscosity and a velocity gradient. So this gives us a hint as to how we can go about it, because if we were to identify with this as one of the stress components, and if we know the viscosity of the fluid, then we can substitute for tau, okay, the corresponding stress here with this expression, and this expression has two components: the viscosity, which is a property of the fluid which can be measured, and this du by dy, which does not introduce any new variables because u is already there. Okay, so we need to describe the stresses in terms of known quantities, and this is a kind of constitutive equation which, for example, here says that the shear stress induced by relative motion within the fluid is proportional to the strain rate. So that is a constitutive law which is being described mathematically here. Okay, so this kind of relations are needed to describe each of these stresses, so that these stresses can be replaced by an equivalent velocity gradients and viscosities and all that. If we have that, then all the stresses would disappear and we will have much fewer number of variables. So we are looking for a constitutive expression for what the stresses are. We can go back to this Newton's law and say, okay, we can replace this, but this is not enough for us, because what is the stress? Okay, so this stress can be identified as tau xy or tau yx, something like that, but what about the other stresses? Okay, so this is for a specific case. This is for a specific case of one dimensional flow, where you have a single non-zero stress that is there. In a general case, this particular relation is not valid. So we have to look for a more generic expression which is able to identify all the stress components in an equivalent way. Okay, so we now search for a constitutive law which describes the stresses within the fluid which are part of the momentum balance equation. We do this by drawing analogy with solid mechanics, because solid mechanics is faced with the same situation, and then you bring in the equivalent to Hooke's law, where you say that the stress is proportional to strain. Okay, so here we bring in the same kind of argument. We say that the stress is proportional to the rate of strain, and why it is the rate of strain is something that we have to see, because fundamentally a fluid is different from a solid in the sense that a fluid will continue to deform as long as there is a stress acting on it, whereas a solid will deform initially and then it will reach a condition of equilibrium with the force applied on this, which is causing the stress, and the deformation which is resisting that force, so that you have a distortion, and a distortion which comes into equilibrium with the force that is applied, whereas a fluid by definition is something that continues to deform as long as the force is applied, and which stops deforming immediately as the force is taken away, okay, for a simple Newtonian fluid, and it does not try to regain its original shape, whereas a solid, for example, if you take an eraser and then try to press it, it will deform, and the moment you take it away it regains its original position, whereas a fluid does not regain its initial position, it will only stop deforming further. So what is important in the case of fluid is not the strain itself, it is the rate of strain. So we will try to relate the stress that is arising in the fluid by relative motion to the rate of strain that is engendered in this. Okay, so and we would like to have a generalization of this stress versus strain relation which is applicable for 3-dimensional flows. So that is what we will consider here to derive extra relations to these stresses, so that we can ultimately have a situation where we have the same number of equations as the number of variables. So that we will do now. It is now making a generalization of the Newton's law of viscosity, which expresses a relation that the shear stress is mu times du by dy, or shear stress is proportional to the strain rate. Okay, in the process of generalization we also want to understand better what exactly we mean by strain rate and what exactly we are modeling in this. Okay, so we would like to consider an expanse of fluid in which we identify 4 particles A, B, C, D, which are such that at time equal to t naught they form a rectangle, and each of these they are at the corners of these rectangles, and they all have their own velocities, as a result of which they are moving along in this flow domain, and after small time delta t the 4 particles will have moved to a different place, and we see after a small time delta t how this initial rectangle has become deformed, and from this deformation we try to find out the strain rate which expresses in a way deformation, the rate of deformation, and we compute this strain rate, and we will see that this strain rate is related to the velocity gradients, and from these velocity gradients we will attribute these velocity gradients to be linearly proportional to the shear stress, and thereby get a general expression for the relation between generalized stress in terms of the generalized strain rate. So that is a strategy, and we will see how it can be done. So we are considering a wide expanse of fluid in which we have 4 particles A, B, C, D, which form initially a rectangle. So let us call this as A, B, C, D. These are particles, all the 4 particles are within the expanse of the domain, and this particle A and B are horizontally separated by a distance delta x, and these are vertically separated by delta y. Okay, so this is also delta y, and this is also delta x, and this is the situation at time t naught. After a time t naught plus delta t, this particle will be moving around here, and this particle will have moved, this particle, and all of them will have moved, so that we now have A here and B here and C here and D here. So we will call this as A prime, B prime, C prime and D prime. These are the new positions of the particles at A, B, C, D after small time delta t. If you now join these, you will see a shape here which is different from the rectangle that we have considered. Okay, we can see that, and this result in the shape of an initially rectangular thing to a more general quadrilateral thing has come about because the points A, B, C, D are not all moving at the same velocity. That is, if there is velocity variation within the fluid domain, that is between A and particle located at A and B and C and D, then there is a corresponding, there is an expectation of a change of shape of this particular initial rectangle that we get by joining all these things. So there is a change in shape if there is a velocity difference, and this change in shape can be identified as being resulting from 3 components. One is rotation, the other is shear, and the third one is extension. Okay. In addition to this, we have a fourth one, which is translation. Okay, so now we can imagine that this is the plane, this is the initially rectangular plane, and we can identify each of these components by looking at this. If all of them are have the same horizontal velocity, then after some time they come like this, they are translated horizontally at a certain velocity. And if all of them have only vertical velocity which is the same, then there is a translation, pure translation in the vertical direction. And if they have the same, if all of them have the same u and v, then they can be moved into this position, which is a pure translation in which there is no the relative disposition of the 4 particles remains the same. So we can say that mere translation or pure translation does not cause any relative disposition of the particles within this fluid. So we can leave this out as contributing to the relative motion. Okay. So now what we mean by pure rotation is, if we have it like this, then the particles are rotating, this whole plane is rotating like this, so that this particle is relative to this, it has moved. Okay. And the rotation need not be about this particular axis, it can be about this axis, or it can be about the center. Okay. So one can see that if there is a different velocities of these particles, you can have something like a rotational motion. If this velocity is 0 and if this has a velocity which is aligned in this tangential direction, one can imagine that this particle is moving like this. Okay. So if there is a coordinated motion of all these 4 particles, you can have pure rotation. Shear is where this particle and this particle, they have different vertical velocities. Okay. For example, if you focus only on this particle and this particle, you see that this particle has less velocity, so it will have moved this much, and this particle has more velocity, because of which it will have gone like this. So the side which was originally horizontal, it has become inclined. Okay. Similarly, this side here can also have different velocity in this direction and different velocity in this direction, in the same direction for these 2 particles. So instead of moving like this thing could have moved like this. So because of which you can see that this side which is horizontal has shifted slightly inclined, and this is vertical has become inclined like this. This is again vertical, it has become slightly more inclined. So that kind of thing is possible when you have different velocities in different directions. Now the third one is extension, which is essentially either the stretching or contraction of this fluid element. So that is, this whole thing, the whole area in a 2-dimensional sense, the whole area of this rectangular domain, it changes between time equal to t0 and time equal to t0 plus delta t. If there is a change in the area of this rectangle and this quadrilateral, then we have extension shear. If there is just rotation, pure rotation, without the change of the angles between these 2 sides, then we say it is pure rotation. If there is no rotation but only the change of angles is there, then we say it is a shear. Okay. So and in the general case, the overall shape may be a combination of rotation and shear and extension. Okay. So the overall change that we see from ABCD to A prime B prime C prime D prime is a combination of rotation and shear and extension that has taken place in the time interval delta t. So we would like to quantify these rotations in terms of the strains. We will identify rotational strain, shear strain and extensional strain, and we will see that these strains are related to the velocities that particles A, B, C, D have at T0, and the gradients of these velocities are actually related to the strain rate, shear strain rate and extensional strain rate, and so therefore we can attribute the change of relative dispersion of these 4 particles to different kinds of strain rates, and we do it in 2 dimensions, but the extension in 3 dimension is similar, and thereby we can identify the change of shape to the gradients of velocity, which is coming in our Newton's law, which is du by dy. Okay, the shear stress is proportional to du by dy. This is a strain rate Okay, what strain rate it is something that we will understand by analyzing the kinematics of fluid motion in this particular way. Okay. Now we have to identify, we have to define, we have to quantify. In order to quantify this rotational strain rate and shear strain rate, we have to define what these things are, and we say extensional strain is when the length AB is different from length A prime B prime, okay, or length AD is different from A prime D prime. So the extensional strain is relatively easy to understand. So this is the change in length divided by original length. Okay, so that is the strain per unit time. Is the extension strain rate, and we can see extension in the x direction only, or extension in the y direction only, or extension in both. For example, extension in x direction only, this is the shape initially, and after some time it becomes like this. So the height remains the same, but the length has changed. And if you consider a strain like this, a change from here to here, this is strain in the extensional strain in the y direction. So one can see extensional strain can happen in x direction or y direction, and there is a corresponding change in length in that particular direction by the original length in that direction per unit time will give us the extensional strain rate. What we mean by rotational strain rate is that we consider the diagonal, and we see if the diagonal has rotated. Okay, so this initially, for example, this may be making a certain theta here with the horizontal. Now the diagonal here is making a theta prime. Okay, so this strain rate is theta minus theta prime minus theta divided by delta t, where theta is the angle that the diagonal is making with respect to the horizontal. Shear strain is by which this particular angle here, okay, has decreased, and you can see that if you say that this particular side AB has shifted so much, and this AD here has shifted so much with respect to this, then the overall initially 90 degrees minus this will give you the new angle. So that is also related to the change in the movement of the angle of this A prime B prime with respect to horizontal, and the angle of A prime D prime with respect to the vertical will give us the shear rate. Okay, so this is with respect to this angle, say delta alpha and delta beta. Okay, we will see what these things are. So we can say that this is half of delta alpha plus delta beta divided by delta t. So these are the ways that we try to quantify. Extensional by the change in length per unit length per unit time, and rotational by the rotation of the diagonal with time, and the shear strain is by how much these things have changed over this. Thanks.